Professor Fernando Rodriguez Villegas from ICTP, who will speak on an update on hypergeometric motifs.
So thank you very much. It's a real pleasure and honor to be part of this event. And I'll thank the organizers for the invitation. So I wanted to talk about something that would be somewhat speculative when I get there. So let me start with the origin of this. Well, a hypergeometric series is the classical power series depending on parameters beta 1, alpha 1, alpha n, beta 1, beta n minus 1. Which these kind of series have played a important role in all kinds of mathematics, in physics, engineering, and the like. Here, alpha sub k is the Pohammer symbol. This defines a holomorphic function in the unit disk. And as I said, various classical functions are expressed in this form by choosing the parameters appropriately. And it was a classical problem to ask when is this series, we call this thing U of t, when is it an algebraic function? By that I mean that there is a polynomial in two variables, so that if you plug in your power series in, say, the second variable, you get 0. And it was proved by Schwartz in a very important and influential paper sometime in the 1800s. He classified all cases where n is equal to 2. And this led to a really remarkable amount of work afterwards. And this later was taken on by Berkes and Heckman in the mid-80s, who classified all cases for all n, so for any n. So this kind of question has interested me for quite a while. And I remember that I was struck by a result by Landau, Edmund Landau, who actually reproved the result of Schwartz using the following fact due to Kronecker. That if we have a power series with rational coefficients, that is algebraic, then the coefficients are basically integers. More precisely, they're integers up to some integer n. So if you scale your coefficients by a power of this number n, so uk times n to the k, then they actually are integers. And Landau used this result in a clever way by looking at the expansion of the geometric, so the hypergeometric series at 0, as in here, but also this function can be continued analytically, or at least it's a branch function, and you can expand it at infinity. And you use this, this statement in both expansions and somehow rediscovered or reproved this result of Schwarz. So the thing that interests me was this connection between the algebraicity and the integrality. And that's what I'll discuss. So a special kind of hypergeometric functions are closer to the kind of thing that one sees in combinatorics. Which are where the coefficients can be, instead of giving in terms of these Pohammer symbols, can be rewritten in terms of factorials. And I'll go into too much detail about this, but let me just say the sum hypergeometric series can be, the coefficients can be written like this up to a scaling factor. And for these, a reformulation of the result of Vickers and Hickman is that the series U with these coefficients is algebraic. If and only if UK is an integer for every k. And there are exactly one more factorial in the numerator than in denominator than in the numerator. So this is really a reformulation of the result, but it makes it very concise. And so, for example, one example I particularly like is something that these numbers that were considered by Chebyshev. I should say that I want to always stay in the situation where the sum of the A's is the same as the sum of the B's. Otherwise, these functions will have essential singularities, and if there's no chance that it can be algebraic. So I will stay in this context. So, and this result is in that context. So if we consider this example, this is both a case where the coefficients are integers, and there's 3 factorials at the bottom and 2 on the top. So according to this is the series made out of these coefficients is actually an algebraic function. And well, you may have heard me speak about this because the example I always use. But I remember when I realized this, I said, well, you know, if it's algebraic, it satisfies the polynomial. So how hard could it be to find this polynomial? It's an interesting question, but if you know a bound for the degrees in the two variables of this polynomial, it is simply a linear algebra problem to find the polynomial. So how hard could it be? Well, it turned out to be a pretty hard problem because the degree is about 4800,000. So I'm not sure I would immediately find it, but if you want to try, okay. So so what I want to talk about is to what extent this type of discussion carries over to hypergeometric series with more than one variable. So let's think about if we had two of these series, W, if we consider the function u of xy, the v of x times wy, it will be an algebraic function. And if we had then both of them are of this form, the coefficients are both of this form, then so the coefficients would be dk times wl. So if we're looking for a criterion of this kind, at least some understanding of the connection between algebraicity and integrality, then it would suggest that there should be two more factorials in the denominator than in the numerator. But this turned out to be too naive. And so...
excuse me,
yes.
The series V, does it have coefficients Vk then?
Yes, it does. Thank you.
Thank you.
I was trying to be consistent with that. So let's go back to Landau. Why did Landau, so what Landau did, possibly inspired by what he was doing in this with this question of Schwarz, was to consider when such ratios are actually integral. So how do we check? How do we check that such factorial ratios?
Excuse me.
Yes.
Don't you need some interlacing condition on?
Yeah.
On something, because you on the right board you wrote equivalence.
Yeah, you do, but it's sort of hidden in here. It's the criterion of Berkes and Heckman involves some interlacing, which I haven't stated. And I'm just saying that that criterion gets translated into this one. You have to do a little bit of work. I mean, it's not immediate, but this is the same. It's really a reformulation of that criterion. It's just the hashing of that interlacing criterion. But I don't want to get into that too much because I want to move forward to the next point. But I can explain it later if you want. So how do you check that something like this is an integer? And this is somewhat of a combinatorialist nightmare because it's not, as far as anybody can see, it's not easy to find objects that this thing counts. So the only way that we know how to, the only general method that we know is to check that the evaluation for every prime p of the coefficient is non-negative for every p and for every k. And what Landau did is to realize that if you have a ratio of factorials of this kind, then this criterion of the evaluation being non-negative is encoded in a function. And he proved that this function has to be non-negative as a real value function. if and only if this happens. So let me show you how that works in the next example. So in the paper where he discusses this, statement is actually a fairly simple statement, but it's kind of nice. So Landau gives this example, which I mentioned in the title of the talk. Let's call this UMN. So 4m factorial. So now I'm moving to an example of two variables. His criterion works for linear forms in any number of variables. And what you do is you write down a formula for the evaluation of this number for every p. And you discover that what you need to do is check that a certain function, so I said, is not negative. Okay, and this function, so this criterion is that this function, which I call L of xy, so a two-variable function, minus 4x minus 4y. These brackets are the fractional part of the real number in the argument. So what you have to check is that this function is not negative for all x and y. So here the function x is the fractional part.
It should be factorial in between. They're in the UMN definition.
On the left.
On the left.
4m factorial.
Yeah.
4m.
What's that in the numerator, Fernando? Just.
The first one, yeah.
Oh, sorry. Let me see what you were saying. Yes, sorry. Yes.
It's kind of funny because you said we need to check something for all p, but your functional doesn't depend on p.
Exactly. That's the beauty. It doesn't depend on p. So this function is the familiar fractional part, which has a graph like this. So it's a periodic function with a discontinuity at the integers. Yeah, so that's the beauty. This function, which is periodic in the two variables, completely tells you what the valuations are of this number for every p. I haven't told you exactly how, but it's a simple way. You use this function to compute the valuation. So Landau's criterion is that if you want to check that this number is integral, as he did, I mean, he gives this as an example of something that is integral, then what you have to do is check that this function is not negative. Okay, let's do that. Okay. So the first thing to observe is because you must observe that this is balanced. So the coefficients of m and n add up. So 4 is 2 plus 1 plus 1. 4 is 1 plus 2 plus 1, right? So it's balanced like the one variable case. So what that means is if you take the derivative of this function, which you can away from the discontinuities, the derivative is 0. So this function is locally constant and periodic. So to describe it, we can do it like this. You'll find that this function has discontinuities at these lines. So these will correspond to a quarter, 3/4, and a half from the 4m factorial and 4m factorial. And then the 2m plus n factorial and the m plus 2n factorial would give you these slanted lines. So they'll slope 2 down and 1 right, or 2 right and 1 down. Okay. And now we can compute the function, because the recipe, I mean, you have to do a little thinking to get this, but nothing is too complicated. Is so this is periodic, so it's enough to do this on a square. And we start with 0, so the value of 0 is 0. And then when you cross a vertical line or a horizontal line, other than the axis, then you add 1. And if you cross a slanted line, you subtract 1. Okay, so then this thing propagates, and you get the whole value of the function. So let's do this quickly. So this would be 1, 1, 2, 1, 1, 0, 0, 1, 0, 2, 1, 0. And I hope you're still with me. 1, 0, 1, 2, 1, 2, 1, 2. I hope I'm doing this right.
Are you computing the values on 0, 1 squared?
Yes, I'm doing that, yes. What I'm doing is computing the values on these regions, because the function is locally constant, and these lines are all the only places where this function has a discontinuity. And then inside the regions determined by these lines, the function is constant. So I'm just writing the value of the function there. And what I'm telling you is the recipe to compute it. Again, you have to check what I'm saying, but it's not so easy. Is that you move up and right, and then if you cross a line, you have to either subtract 1 or add 1, depending on whether the lines are the vertical or the slanted ones. And the axes don't count. So this is a function on the torus because it's periodic in the two functions. So this region is the same as this region. Yeah. So this thing sort of folds this way and folds this way. So voila, all the values are non-negative. So we just proved that this number is an integer. Okay. So the corollary of one corollary of this Landau criteria is that there's a finite process to determine if these things are integer. A priori, there are infinitely many conditions, infinitely many m and n, but this shows us that it's a finite process. And so there's work that I recommend of Saldarajadam on the one variable case. And he, at some point, told me that some of his students got tired of doing this and so refused to do any more examples because it was too boring. All right, so and I've stared at this picture for a while, and I still think that there's something hidden that I haven't discovered. So I'll leave it there for you to look at. Okay, so yes.
What is suggestive formula? So you can write it with more variables.
Yes.
And in dimension 4, you will not have those beautiful pictures. How will you do it then?
Well, I won't be able to draw the pictures, but it will still be finally many collections of polytopes. I'm not saying that. I think a computer can be programmed because, I mean, I think it's an interesting question, actually, computationally, how you would do this. Because you would have to find some description of this polyhedral decomposition of the cube or in the right dimension. And then all you have to do is pick a point in the middle and find that it's not negative there because you know it's locally constant. So it's definitely a finite problem. Now, how do you do this in a computer effectively is a different question, which would be interesting, I think. I don't really have a full answer. So yeah, I mean, you could say, write down a a linear combination of fractional parts of linear forms, how would you efficiently determine if the function is not negative? Okay. So continue on with things we associate to this. Now I want to associate to this. Well, let's write down what linear forms we're talking about. So I'm going to write them like this. I put a negative sign to the ones on the top and a positive sign on the ones at the bottom. So I'm just recording what are the linear forms that we used. So let me call this thing gamma, this function, this matrix. And now I'm going to consider a sort of dual of this, maybe the Gale dual would be more appropriate. So I'm going to consider 6 points in Z cubed such that these gamma ij's, the rows of this matrix, are linear combinations that gives us 0. Now, the sum, you can see that because of the balance condition, the sum of the rows is 0. So if I add any vector to these m's, the equation still holds. So this is really an affine relation. And I want to pick this in a sort of a minimal way. So one way to say that is that if I consider the convex hull of these points in C3, which will be a lattice polytope, that it has minimal volume. And if we do this, of course, the m's are far from unique, but they are unique, and therefore the polytope is also unique up to invertible affine transformations with Z coefficients. So it's canonical to that extent. And so what is this polytope? Well, it's not hard to find a choice of m's. Let me write it down. So possible choice. This. And it turns out that these 4 points here are the vertices of the polytope. And these are interior to two-dimensional faces. So the polytope is in fact a simplex. So I'm drawing this not in scale, just to illustrate. So we have 4 points that are vertices, and then 2 points that are in the middle of 2 of the faces. Okay, so you'll see where we're going with this. At the moment is some other object we associated to this data. But this polytope, in fact, encodes some more invariants. which is what I want to uncover. Okay, so let me make a parenthetical discussion. So suppose we have, in general, a lattice polytope in d dimensions. We'll apply it to our example. Then one usual thing that we can do with it is compute its Erhard series. Which is the generating series where you, for each dilation, you take the polytope, you count how many lattice points it has, then you take twice the polytope, you count how many points it has, and so on, and you make a generating series with them. So Erhard showed that this is the expansion of a rational function of the form of this form. And here H, and this I think has become the standard notation, which is sort of weird. The numerator is a polynomial of the form, so it has degree at most d. It has certain coefficients hi, ti, and the hi are non-negative integers. So this is, I don't know, part of this is due to Stanley, part of it is due to Erhard.
Sorry, could you repeat what the coefficients mean?
So you take your polytope and you count the number of lattice points. So only those with integer coefficient entries. Then you double it, so you get a bigger polytope, and you do that again. You count the number of points there, then 3 times and 4 times, and you keep doing it. And you, at every stage, you count how many points you have.
Fernando, shouldn't there be some ingredient in this formula which corresponds to points on the boundary of the polynomial?
No, as it is, you're going further into a different direction, which is to connect the number of points of the polytope to those in the interior. But no, at this point, at this stage, we don't need anything else.
But your polytope is closed or open.
Yeah, is the convex hull of a certain number of lattice points, with all the phases included. So one thing that I should have mentioned about this is that this has no interior point, lattice points. And the speculation that what I want to make, because of what I know happens in one variable, although I didn't go into a great deal to explain it, is that this fact is actually, in fact, equivalent to the integrality of the coefficient. Okay, so, but let's go back to this general situation. We have this series, and by counting points on the dilation produces this H, which is an invariant of the polytope. And these numbers are very interesting. And there's a bunch of things that we know about them. So, well, I already mentioned that the coefficients are non-negative integers. H0, the constant term is 1. The highest coefficient, or at least in principle, possible highest coefficient is the number of interior points of the polytope. the value of the polynomial at 1, so the sum of all the hi's, is the volume of the polytope, volume sort of normalized so that the standard simplex has volume 1. And the thing that is more important for this discussion is that a further property is that if we define the codegree of delta to be the smallest k, such that k delta has an interior point, has an interior lattice point, so the first time, well, the polytope may have no interior lattice point. You dilate it twice, it may still not have any lattice points, and you keep doing this. At some point, you will have one. So your first time that happens, you call that the codegree. And it turns out this codegree is called a codegree because it's related to the degree. So the polynomial on the numerator of this rational function can go all the way to degree t to the d, but what's missing, what might potentially be missing, is exactly how far you have to multiply before it acquires an integer point inside. So for an example, so you can compute this in magma, for example, which is does it really quickly, is pretty amazing. So you can compute the case for our Landau case, our Landau polytope that we've been discussing. This polynomial is 9t squared 6t plus 1. So it lives in 3 dimensions, so it could have had a t cubed coefficient, but it doesn't, and that's exactly because it doesn't have an interior point. But it does have an interior point if you double it, so that's why you see there's 9. And you can,
here.
what's that?
What is here?
This is a 9.
Ah.
Sorry, my numbers have deteriorated over time. The volume is 16, and the codegree is 2. Okay, so why are we doing this? I'm going to now associate to this picture yet another thing.
So a question.
Yes.
Are you saying that we get some coefficient for t squared because when we double, or specifically the 9 we could expect?
No, it's not so one-to-one that 9 is the number of interior points, but if the number is non-zero, it's because there will be at least one interior point. I forget, there is a connection, but I forget what it is exactly. Okay, so the final thing I want to associate to this data is something coming from algebraic geometry. Yeah, maybe I think I forgot to say. Let me try to back up a little bit. Let me recap just a little bit. So we had these numbers that Landau tells us, or we proved ourselves that they're integers. What I mean integers, of course, is for every m and n. So, and the number of linear forms on the top is 2, and the number of linear forms on the bottom is 4. So the difference is 2. So it may suggest, according to what I was arguing earlier, it could suggest that this function is algebraic if I form a generating series with these numbers. And I claim it isn't. So if this is UMN, I form the generating series UMN x to the m, y to the n. Let's call this thing u of xy. This is not algebraic. So a naive generalization of the criterion I had in this part of the board does not work. It's not true. And the reason is simply that if I set, for example, y to be 0, then this function still remains to be algebraic. But if we do that, we get a one variable form quotient of factorials. But now there's 3 in the denominator and 1 in the numerator. So this is not an algebraic function. So it could mean that the 2 variable one cannot be. So I found this puzzling because there has to be something of the sort an algebraic, something algebraic is lurking in the background, and I wanted to understand what it is. Okay, so we'll get there hopefully. But so now let me go back to this algebraic geometry. So I will associate to this whole data a family of varieties of a hypersurface, a family of hypersurfaces in the 3-dimensional torus. And simply what I'll do is take the monomials that we had. We had 6 monomials, 6 vectors in C3, and I think of them as monomials. And I consider the equation sum of ui x to the mi equal to 0, where ui are for the moment just arbitrary parameters. So this is a 6-dimensional family of hypersurfaces in the torus. And I use the torus because the mi's could have negative entries. So this is really a Laurent polynomial. Now, this family of varieties a priori has 6 parameters, but it's easy to find that that's a little bit an overkill, because one thing you can do is you can take the variables and scale them without changing much of anything. And you can take the polynomial, say it's f, and scale it as well. So if you use this scaling, you'll see that you only have 2 parameters left. And so this really is a 2-variable, intrinsically 2-dimensional family. So let me concretely write it down. And I'll use, I'll write it in a homogeneous form already. And I'll use the parameters, I call them T now. There's 2 of them. So that's what happens after exploiting the scaling. So if you clear denominators, and consider this equation a priori only defined in the torus, but think of this as embedded in P3. What we obtain is a family, say Z bar, in P3 of quintic surfaces that have 2 singularities. at 0, 0, 1, 0, and 0, 0, 0, 1. So if you take these singular surfaces and resolve the singularities, what you find is some somewhat exotic algebraic surfaces called Enrique surfaces. So that was a bit of a surprise. These, you don't just encounter these by walking down the street. So that's somehow the fact that they appear this way is a bit strange. So now I have to make a big leap. How are we doing with time? I think
12 minutes.
Huh?
12, 13 minutes.
12, 13, okay. So let's look at these. These are affine. So these are affine hypersurfaces in this torus. And I will cut through a lot of theory to get to some geometric invariants that we can associate to any algebraic variety, non-compact, non-smooth, of whatever kind. And I will not try to even give too much of a hint of where these things come from. But the result is, we take it as a black box, is there's a triple index series of integers, positive integers, not negative integers, called having to do with the mixture structure. So I'll say just a few things about these numbers. If Z, or let's say X, happen to be smooth and compact, so usual smooth compact manifold, which is an algebraic variety, then only those numbers where I and j is equal to k are non-zero. But otherwise, this is a truly sort of triple index sequence. So, for example, for these Enrique surfaces, let's say that this is our x. Then, if we look at these numbers for k equals to 2 for the second cohomology, then they are 0, 10, 0. So this is H20, H11, H02. So, so this is in the world of algebraic varieties, but when the varieties arise in the form that we have them, maybe it's time to erase this. That is, when they come as hypersurface in a torus, then there's techniques that apply to them that are specific to this. And it was Danilov and Kovansky in the early 70s that relate these numbers to the polytope. So to the Newton polytope of a defining equation. So a hypersurface in this torus is given by some Laurent, the zero locus of some Laurent polynomial. like this one, say. If you look at the exponents of the variables, you use those as points in a lattice, and you consider the convex hull. That's the Newton polytope. And then there is a relation between these geometric invariants, which a priori are, this is a different story. They are in the world of algebra geometry, nothing to do with Laurent polynomials or anything else. When they arise in this form, they are connected to the geometry of the polytope. And so if we consider, so take Z to be our surfaces. So some generic member of this family, this depends on T1 and on T2. This will be a smooth surface, but non-compact. We're looking at it as a subvariety of C star cubed. And you can work out what this mix of numbers are. And I'll write them in this form, the way Danilov and Kowalski do. So these are the numbers associated to the second cohomology. And I put the number ij in the spot ij. So the H112 is 5, the H02 is 4, and so on. 01 is 4, and so on. And so a connection between what we did before and there.
Could you repeat, because connection broke?
Yes. Okay. So I'm not sure how far back. Not the beginning.
Well, I don't know about those numbers in the most left.
Here.
And even most left. No. 0961. How do you get them?
I'm adding these adding the rows. So I'm adding the numbers on each row of this triangle, and that much I think we can see. What I want to point out that these are the same coefficients. These are the coefficients of this H star polynomial that we had before. So this is the H star.
It's obvious that they were non-negative to begin with?
Yeah, they were non-negative. These were known to be non-negative, independent of anything. And yeah, that was proved handy, I think.
And the polytope comes from the polynomial which defines the hypersurface, right?
Exactly.
I think you missed the word there. A Newton polytope of a polynomial defining Z.
Equation.
Equation.
Yeah. Yes, thank you. Equation for Z. Okay. And the reason is that these numbers are not enough for what I want to point out. We really need this extra sort of dimension to this story, this refinement. Now, an important thing, and I see if I can say something about this, but these diagonals are the value of I plus j, and so I plus j, so we have these numbers h, I, j, k, and I plus j is what's called the weight. So I mentioned that if you have a smooth and compact variety, the weight in this definition is always equals to k. But in general, the weight will vary. And in the smooth case, as we have here, the weights are all below the k. So k here is 2. And so we have weight 2, weight 1, and weight 0. And so each individual piece of a given weight is an interesting thing in its own right. And I'll see if I can make sense of the following. I claim that the algebraicity that was lurking behind the example is the fact that these numbers are 0, 5, 0. Okay. And so let me try to make sense of this. So it's not like in the one variable case that the integrality plus this number of factorial difference implies that the function itself is algebraic, but something else is algebraic. And the claim is that what happens is that the top weight part of the cohomology only has a non-zero Hodge number in the middle. So I know this, I'm not sure I'm going to make a lot of sense, but let me try. But I think I'm pretty much out of time. Yeah, I have 3 minutes, so let me really quickly go through this. And the final stage, like a big tutti of the orchestra, is arithmetic, right? As it should be. Well, I'm biased. We can try to count the number of points of this variety, this surface, over finite fields. Okay? Now, when you do that, you find that you can relate this number of points to a finite sum that is a sort of finite field version of the hypergeometric series we started with. So I'm definitely not going to try to explain this in detail, but I hope you see a little bit of what might be behind. The factorials is very well known all the way to Jacobi that are related to Gauss sums. And so when you compute the number of points of the surface, you'll see that you need to involve this expression, which is involves Gauss sums in the same shape as the coefficients of the series. And so, on the other hand, we know how to compute the number of points on a variety by means of the Grothendieck-Lefschetz trace formula. And that formula, what it tells you is that you have to take an alternated sum of traces of Frobenius acting on cohomology. And the point is that if you have something of weight W in your cohomology, then the contribution will be a sum of numbers from 1 to the dimension of the space you're considering, and the weight translates into the fact that these numbers are of size q to the weight over 2. So just to finish quickly, when you look at the contribution to the number of points from H2, there'll be something of weight 2 coming from here, something of weight 1, and something of weight 0. So the part of weight 2 is something that has only one Hodge number. So this is this kind of thing that you expect to see coming from something from an arcing motive, and that should correspond to an algebraic function. So I think I'll leave it at that, just to say that it's not like the original series is algebraic, but there is in the space of solutions to this to the differential equation that this satisfies, there is going to be something of dimension 5 that will contain an algebraic function. So I'll leave it at that. Thank you.
questions. So maybe we start from Kiev. So do you have some questions?
Do we have some questions? Okay, I have a question. Was this, in the end, a hint on how to construct this algebraic function?
Yes, in a sense, but not that I'm hiding anything. It's just I haven't. I'm giving something that's not finished. I mean, so this is, yes, indeed, a hint of where the function should be. And I have some thoughts of how to actually get it, but I don't have the full story yet.
In the beginning, you mentioned Chebyshev example and this big number, the degree of the function. So if you succeed, you will somehow see the degree, right? You will explain it.
Well, in the case of Chebyshev, you can explain the degree because what happens there is that the GABA group involved is a reflection group, and so computing degrees in the reflection, you have the Chebyshev series is a vector in this lattice, and so you have to look as a stabilizer. I mean, I explained this in this paper I wrote. It's not difficult to actually explain why the number is so big. I mean, it doesn't mean that you can use that to compute the equation. It's Galois theory. I mean, you have to look for the index of the stabilizer of that series in the lattice. And that, because it's a reflection group, is actually not difficult to do.
Thank you.
Thank you. So, do we have a question here?
Well, so far we have answered mostly linear forms, right? But what if we consider affine, like for one variable we have Catalan numbers, which are also integers and which also produce algebraic?
Yeah, I think that's an interesting question as well. You can think of putting linear forms as either differentiating or integrating. So I think that maybe that's what you have to bring in. But yes, that's an interesting direction I don't know much about.
Other questions? Here? Yeah, please.
Very naive. So is there this Archive polynomial that you control the number when it's inside, which comes from the algebraic function? Is there analog if you instead of multiplying by k, take a subset, take one set plus another set? Does it have any interpretation?
You mean from different polytopes? No.
I take polytope plus polytope to itself rather than multiplying by 2, and then taking k times. Is there any algebraic interpretation?
I think I think if you get a new polytope called the Minkowski sum. I mean, I guess you're asking the number of lattice points of the Minkowski sums.
Yeah, whether there is
I personally don't know, but there may be something. Yeah, no, I think it's interesting. I personally don't know. Yeah.
Thank you.
Does giving this decomposition of the numbers as Hodge numbers, does it do more things about the numbers? Like some opportunity you get a more numerical constraints on what the numbers can be?
Yeah, as you can see here, the numbers are symmetric, so that definitely has to be built in. The other thing is that because the variety is smooth, the weights, as I mentioned, have to go down. No, and there's nothing up. I mean, a priori it would go all the way to twice the weight, but then there's nothing up there. Besides that, I think, I'm not sure. One thing that, yeah, so I'm not entirely sure, for example, if the, what's the relation between, this part is somehow the more interesting one, that has to do with the full polytope. The other things have to do with faces of the polytope. And you can think of them as error terms. So if you're trying to count points, this is sort of the interesting part. Now, whether the degree of this part has to be the same as the degree of the whole thing. So things like this, I think there's more questions than answers about it.
You also get some unimodality in some Lifshitz.
Well, but this is everything is open, right? So hard Lifshitz, would be maybe tricky. I mean, there's been actually worked on cases where you seem to have some kind of this curious symmetries in affine varieties, but it's not general.
Okay, so if we don't have other questions, let's thank Fernando again.
Thank you.